Let's begin by analyzing diffusion in binary mixtures of components 1 and 2. Let U1 and U2 represent the velocities of motion of components 1 and 2 in a laboratory fixed reference frame. U is the molar average mixture velocity. Since the chemical potential gradients are constrained by the Gibbs-Duhem relationships, only one of the chemical potential gradients is independent. The mole fractions sum to unity, and therefore there is only one independent measure of composition. In the Maxwell-Stefan formulation, the force acting per mole of species 1 is balanced by friction species 1 experiences in undergoing relative motion with respect to species 2. The frictional term must be proportional to the composition, and we take that proportionality to be represented by the mole fraction of component 2. The physical significance of the Maxwell-Stefan diffusivity, where we use the symbol D with a line through it, is that it represents an inverse drag coefficient. The force acting per mole of species 1 is a negative of the gradient of the chemical potential with the units newtons per mole. The Maxwell-Stefan equation can be reformulated in terms of the diffusion flux, which is defined as the flux with respect to the molar average reference velocity Vm is the molar volume of the mixture. Rather than use the chemical potential gradient as a driving force, it is convenient to define a thermodynamic correction factor given by this expression, which quantifies departure from ideality. Indeed, if the activity coefficient is unity, gamma is equal to unity. And the Maxwell-Stefan equations can be recast into the form flux of component 1 is proportional to the mole fraction gradient of component 1, and the constant of proportionality is the Maxwell-Stefan diffusivity times gamma. Therefore, in comparison with the Fick's law, we note that the Fick diffusivity equals the Maxwell-Stefan diffusivity times a correction factor that quantifies departures from thermodynamic idealities. For interface mass transfer between two adjoining phases, the X phase and the Y phase, we may define the mass transfer coefficient, say, in the X phase by this expression, where we assert that the diffusion flux is proportional to the difference in the composition between the bulk and the interface, and that difference we denote as delta X1. K is the mass transfer coefficient, and if we use the factor 1 divided by the molar volume as a pre-multiplier, the units of the mass transfer coefficient is simply meters per second. So the diffusion flux is moles per square meter per second, and the units of the mass transfer coefficient K is meters per second. It now remains to derive the physical interpretation of the mass transfer coefficient. From the previous slide, we note that the diffusion flux is written as a product of the three factors. The first one, 1 divided by Vm. Vm is the molar volume. Mole fraction of component 1 times the velocity difference between the velocity of transport of species 1, and U is the molar average velocity of the mixture. From this expression for the mass transfer coefficient, we can equate these two expressions for the diffusion flux, and we derive the expression for the mass transfer coefficient in terms of the difference in the velocity for component 1 with respect to the mixture divided by the driving force for component 1 divided by the mole fraction of component 1 in the bulk phase. Now, the magnitude of delta x1 divided by x1 should be less than unity, and therefore it follows that the mass transfer coefficient should be greater than the velocity difference between component 1 and the mixture. The physical significance of the mass transfer coefficient is that it represents the maximum velocity with respect to the mixture with which a component can be transferred from one phase to the joining phase. For background to this derivation, I refer you to my paper, Physical Significance of the Mass Transfer Coefficient, published in Chemical Engineering Journal in 1987. See also my textbook, Multicomponent Mass Transfer, that was published in 1993. Some other videos on the subject of diffusion and mass transfer are listed here, and these are all available for viewing on my YouTube channel.